So what we're going to do now is continue with our overview of Spring, and we're going to turn our attention to something called SpringWebMVC, which stands for Model View Controller. And this is one of the stacks that's available with Spring Boot, and we'll talk about this one first, and later in the semester we'll come back and talk about the so-called reactive stack. But the MVC stack is built on something called servlets, and it uses synchronous blocking I/O with a one request per thread model using a thread pool. And we'll talk about that because those are some things that have changed a bit over time with the advent of the new Java 19 features. So in this discussion, we're going to focus first on SpringWebMVC's concurrency model, and then we're going to talk about its communication model. And both of these concepts are very important for the assignments we're going to do, particularly the communication model for assignment 1A. But we'll start with concurrency. So SpringWebMVC concurrency uses something called synchronous input-output, or synchronous I/O. And what that means, as we'll see in a second, is that when a client makes a call, it will block waiting for the result to come back. And the other piece of the puzzle here that's important to understand is that SpringWebMVC on the server side uses a one thread per request model. So what does it mean to have a one thread per request model? What does it mean to block, and so on? So what it means is that each request is handled by a thread on the server side that blocks until it's able to fully process the request. So imagine we come in here and we're writing some application to get a list of airplane flights. Right now, the air traffic control system in the US is down, so it'd be hard to find any flights, but assuming it comes back up again at some point, you go out and you make a call from a client, mobile device, web browser, whatever, goes to the server and says, find me a list of flights. Server goes off and looks up in some databases to get the results, and then it returns a list. And after that call is done, the client could make another call to find some different flights. And then the server would go off and do some work and send back a result. So pretty straightforward way of doing things. The issue here is that the call and response model would take a little time because we have to wait for the server to get the results and send them back to the client before the client thread can unblock. Now, there are some benefits of having this blocking request response stop and wait style protocol. And one of them is that blocking calls are a natural form of back pressure. What that means is that the server is not going to send the data back to the client faster than it can process it because the client has to wait till it gets the results back before it can make the next request. And you might think, well, what's the big deal? Of course that's the way things work. Well, we'll see later that forcing the caller to wait is not the only way to build software, not the only way to build web-based systems these days. But the nice thing about it is it eliminates the need for end-to-end rate control. So we don't have to worry about limiting the rate at which the server sends the data back to the client because the client is only asking for one chunk of things at a time. We'll talk about alternative ways of doing this later. One of the consequences, however, of this design, this synchronous blocking I/O approach, is that the server will need to have a bunch of threads in order to handle bursty clients. What are bursty clients? Bursty clients are things that occur in clumps. So, for example, when the FAA announces that the air traffic control system is down, all the people who are trying to travel immediately get on their phones and start trying to call their carrier, the airline, or try to see what's going on, and that leads to bursts. A bunch of things show up at once. And of course, we'd like to, as much as possible, be responsive if we're building servers, so we have to have lots of threads in order to be able to have all those requests be run. The problem, of course, is there typically, historically, have not been as many cores as there were threads, number one, and clients need threads too, so there's lots of threads. And in traditional environments, like traditional operating systems, traditional versions of the Java virtual machine prior to Java 19, the issue was that each thread that you allocated would be associated with an operating system kernel level resource, which is also called a thread, a kernel thread. And that takes a fair amount of memory. It's about a megabyte of virtual memory per thread in the operating system. And so things kind of came to a screeching halt if you had lots and lots of threads. So the way that this has historically been solved in things like SpringWebMVC was to have a pool of threads that were limited, maybe to a couple hundred. And that way you could bound the amount of resources that were dedicated to this. The good news is that Java 19's virtual threads provide much more scalability than we've done heretofore. And so we'll see later in the course, we'll start using virtual threads to write server-side code, and that'll help to allow things to scale up much more nicely. Let's talk a little bit about SpringWebMVC communications. That's what you're going to be encountering right away with assignment 1A. We won't get to concurrency till just a little bit later, but assignment 1A will focus on communications and sending data. The nice thing about SpringWebMVC is it uses common Java types to communicate from client to server. So collections of various sorts, lists, sets, you have maps, and so on and so forth. And you can pass these as parameters, and you can return them as return results from method calls that are called across the network. So you can have Java strings and integers. You can have lists and maps. So we can have, for example, here's a method that's called an endpoint handler method that will get a list of airports in a microservice that supports airline reservations or airline listings and so on. So you could say, please get me the list of airports. It'll give you back a list of airports. So list is a good Java collection, and that can be programmed both on the client and the server side without you having to do a lot of extra work. The endpoints in SpringWebMVC can send and return Java collections in one fell swoop. Rather than having to make lots of individual calls for each element of the collection, you can send a request that includes a list. You can get a result back that includes a list. And you can see here when we get the list of airports, the client says, hey, server, give me a list of airports, and it gives you back a list of airports as one element, one collection. The downside with this approach, however, is even though it's easy to program, is that client latency may suffer a bit because we have to return this in one fell swoop. And so the client has to wait for the server to collect all the information in that list and send it back. Moreover, memory will be needed to store the entire list on the server, in the intermediate buffers, and then back on the client. So there may end up being, especially if you have a large list, you may end up taking a large amount of memory, which could be a problem. This particular issue of having to wait for all the data to be conglomerated together before it can be sent back to the client is addressed in SpringWebFlux by using reactive programming types, such as fluxes. We'll talk about what a flux is later. But a flux is essentially an asynchronous type where the elements in a flux can be streamed back to the client without having to wait for the entire server to buffer everything. So you can send it back incrementally, which could be more responsive. And we'll talk more about that when we get into the asynchronous part of this course. So that's the end of the overview of SpringWebMVC, just to give you a little context of what we're going to talk about next.